All right, now it is time for particle-particle equations in stoichiometry. Now remember, there are three different kinds of particles that we can talk about, and that is like on the atomic level, atoms, okay, which are going to be your elements that are listed on our best friend periodic tables. There are molecules, which are going to be all of your non-metal covalently bonded compounds. And then there are your formula units, our FUs, which are going to be all of your ionically bonded metal nonmetals. So you might see molecules, atoms, or formula units. I call them MOATFU. Okay, so these are non-metal covalent. All right, so the given and the unknown are both in those units, molecules, atoms, or formula units. And just like we have seen with mass-mass or with volume-volume problems, okay, you have to convert whatever this is, whatever this molecule, atom, or formula unit to moles. It is the same conversion factor, and that is Avogadro's number, which is 1 mole equals 6.02 times 10 to the 23rd of anything. Mole problems. Then we use our mole reaction ratio. This is what we always use in stoichiometry because all of our equations are based off of the moles. And then we convert our unknown back into the representative particle that we want in the equation. All right, so if we review our mole roadmap, we are going to be looking at this section right here and moles. All right, so our particles are our molecules, atoms, or formula units, and we'll be going this way. First, getting rid of particles by dividing by Avogadro's number, and then getting to moles, then doing the reaction ratio, and then getting our unknown back into particles because we would then use 6.02 times 10 to the 23rd over 1 mole. Okay? So with this, this is our general game plan of what we're going to see. Our given particles will either be molecules, atoms, or formula units. We will use 6.02 times 10 to the 23rd and then be specific if it's a molecule, atom, or formula unit per 1 mole. Then every stoichiometry problem uses the recipe from the balanced equation. That gives you the reaction ratio, the moles of your given for the moles of your unknown. And then we get back into our particles, whether it be a molecule, an atom, or a formula unit, by multiplying by that and dividing by 1 mole. Okay, so a sample problem looks just like this. We have our formation of NH3, our synthesis reaction. N2, we have to make sure it's balanced. 3 H2s make 2 ammonias. And here we are looking at how many molecules of hydrogen are needed to react with 3.784 times 10 to the 25th molecules of ammonia. Okay, so we are going to be using 3.784 times 10 to the 25th molecules of NH3. Now, remember, MO is molecule, MOL is mole. All right, so that's a little thing to always keep in the back of your mind. This is going to be our given. Then we need to convert from given into our moles of our NH3, and then we want to know how many molecules of H2 is it going to take. This is our unknown. All right, so what is our conversion factor? Okay, our reaction ratio is from the balanced equation. it is 3 moles of hydrogen from the balanced equation for every 2 moles of NH3. Okay, so let's write out our game plan and follow it along. Okay, so the game plan always starts with your given particle. Then we're going to multiply by Avogadro's number to get into moles. Then use the reaction ratio to convert moles of given to moles of unknown. And then multiply by Avogadro's number again. All right, so our given particle from the equation is 3.784 times 10 to the 25th molecules of NH3. Make your 3 conversions. First, we want to convert molecules into moles. So it is 6.02 times 10 to the 23rd molecules of NH3 for every 1 mole. That's a given, steady, constant conversion factor that you always know. That's a definition of a mole. And then we are going to use our reaction ratio to convert our moles of H2 and our moles of NH3 to and from one another. So if you have your moles of NH3 here, the moles of NH3 from the balanced equation goes on the bottom, and then 3 moles of H2 goes on top. All right, so cancel out moles of NH3, cancel out moles of NH3. It's like all the other dimensional analysis problems. And then lastly, 1 mole of H2 needs to cancel out those 3 moles, and then we use Avogadro's number again. 6.02 times 10 to the 23rd molecules of H2. And then moles and moles cancel out. Okay, quick, go grab your calculator. Don't use your phones because it's not going to do the times 10 to the correctly. And we're going to push pause if you don't have your calculator to go and make sure that you know how to type this in. Okay, do you have your calculator? Hope so. So we multiply everything on the top and we divide by everything on the bottom. So that is 3.784 E25. Remember, the E button, even though it's EE, only comes up as E on the calculator and represents the words times 10 to the. There should be no carets, all right? This is going to make sure that we do the correct orders of operation, PEMDAS, so that we don't end up having an incorrect exponent in our answer. So 3.784 E25 should be on your calculator screen, times 1, times 3, times 6.02 E23. Then we divide by the denominator, 6.02 E23, and then we divide by 2 and hit enter once. So when you put this in the calculator, you should get 5.676 times 10 to the 25th molecules of H2 as your final answer. This has 4 sig figs, this has 4 sig figs, and that's what you want to go off of. So did you guys notice what we noticed in our volume particle or volume problems that we did in the previous video? Okay, this step and this step cancel each other out. Yes, you still have to show the work, but you could skip plugging this into the calculator altogether and simply just type in this part times the ratio, which is 3.784 times 3 divided by 2, or 3 halves, and you get the exact same number. So up to you, that's a little life hack, and that's a little bit easier of a way in order to solve this without having to plug everything into the calculator. All right, to go over the problem again, 3.784 times 10 to the 25th molecules is our given. Our molecules of H2 are unknown. Mole ratio MOL is mole, MO is molecule. 2 molecules of NH3 from the balance equation for every 3 molecules of H2. And we have to use Avogadro's number, 6.02 times 10 to the 23rd, to get from one to the other. So then we plug in our given particle, which is 3.784 times 10 to the 25th molecules. We use Avogadro's number in order to convert it into moles. So molecules and molecules are going to cancel each other out. Then we use the mole ratio. So if we have 1 mole of NH3 here, we put the moles of NH3 on the bottom and 3 moles of H2 in the numerator. And then lastly, get rid of the moles of H2 by putting 1 mole of H2 on the bottom and 6.02 times 10 to the 23rd molecules of our unknown up top. All right, so little pro tips for you, just like we've seen before. These are your given particles. Okay, this will be Avogadro's number of your given in the denominator every time. 1 mole of your given up top. In your reaction ratio, since you're getting rid of the given, you're going to see that the moles of the given will be on the bottom in the denominator, and moles of your unknown will be on top in the numerator. And then lastly, 1 mole of your unknown will always be on the bottom, and you will see that Avogadro's number of your unknown will be in the numerator. And like we said in the previous slides, this step and this step are a formality. Yes, you do have to show the work, but it's the same as it not being there, and simply taking your given value and multiplying it by the ratio to get your answer. Okay, be careful with your scientific notation. E means times 10 to the, but you shouldn't have any carrots. You are not bunny rabbits. You are better than that. Okay, good luck, and thanks for checking out particle-particle conversions.